Okay, so welcome back to the last and final session of this 2-week-long program, School Come Workshop on Data Analysis and Cosmology. In this session, as you know, Professor Dhiraj Kumar Hajra will continue his discussions on dark energy. Okay, so there is a request to all of you, please be there till the end of the program because we have some formalities to do, then only we'll end the session. So please be there till the end of this session because this is the final session. Okay, over to you, Dhiraj.
Thank you, Supervisor. Okay, let me just take 1 minute to set up and also send you the link for this presentation. Okay, change everyone with the link. Copy link, done. So this is the dark energy 2 slides. These are the dark energy 2 slides that are appearing in your chat box. Yeah. Let me just share screen. Okay. You will notice that in the Psi server, inside this notebooks directory, I have uploaded TIH4DE2. Okay. This is the 4th hands-on session and dark energy 2. So that is why. Give the name. Let me just make this change now so that we do not have any confusion later. Theory constants as constants. So you can simply download. I have saved it, so you can simply download that in your directory. And okay. And if you have problems with Psi server, let me upload it here as well. So okay, this is okay. It is uploaded. You can download from here as well in the chat box. And this if you are doing it in your local machine, then possibly you don't have to change constants to theory constants. All right. Okay, so let me just start with from the point where we left yesterday. So there were 2 questions. Okay, I'm sorry. There were 2 questions that were partially answered. Okay, and one question I answered, but I wanted to show the plots. I mean, just to show you that the absolute magnitude are actually of the same order. And another question for which I was not really happy with my answer. So I have explored that in a little bit more detail, and I have prepared a slide for that. Okay, so one student asked that what is the reason for the how do we know that the peak brightness or the absolute magnitude is constant for all supernova? Okay, yesterday when I said supernova, I was just talking about just type 1a supernova, IA supernova that I discussed. It was written in the slide, but I didn't mention it properly. So I mean, you can find certain theoretical explanation of Chandrasekhar limit that when it becomes 1.4 solar mass, a star becomes 1.4 solar mass or something like that, then the existence of supernova, I mean, then the generation process of supernova takes place, etc. But I mean, there are many other things. There are many other effects, not just that, that can change the absolute magnitude. So, I mean, what usually people rely on the observations here more instead of just having one theoretical explanation. So, for example, when you take the supernova, supernova actually starts for, I mean, happens for a few days, all right, and it starts in, okay, as you can see, I have plotted it here, and the reference is Kim et al. 1997, that is given here. It starts off and its brightness increases. At some point of time, it reaches after a few days, it reaches peak brightness, and then it falls off. Okay, and you can see that the peak brightness and is correlated with the decline. So you see, if the peak brightness go fainter, so fainter supernovae are actually have a sharper or faster decline rate of the absolute magnitude. Okay, so this is what it is written. Okay, it is the B band absolute magnitude minus 5 log and then h by 65. This is a parameter which comes in the light curve, for example. This is the what you do is that you analyze this light curve of supernova, individual supernova. So as I said, the peak brightness is correlated with the decline. So here a lot of analysis is involved. For example, how to fit the supernova light curve. Salt does that. I mean, there are codes that does the principal component analysis in order to fit these curves. And then what they do is that they use a stretch factor. So they just correct for this peak brightness and decline rate correlation, and they apply stretch factor. Once they apply that, they find that all the supernova, they are, for example, they are the different at all the supernova, the peak brightness are actually matching. Okay, for example, 0th day is the day of the peak brightness, and you basically count from negative days. For example, when you see the first illumination, and then after a few days it just dies down. Okay, so this is the observational. These are the observational signatures that shows that the supernova has the same or similar peak brightness. Okay, now if the student is present here who asked me this question about the peak brightness, does it answer his question? I forgot the name of the student who asked me. Is he present? No? Okay. Now, another question was why the supernovae are the covariance matrix or the distance modulus covariance matrix that I showed is correlated. Okay, because the question was because the error we are talking about individual or independent supernova that happened at a different point of time, and why their error bars or why their data points should be correlated. That was a really valid question. And I gave this answer that since we are doing, doing it in the same framework, allowing them all to come in the same umbrella of analysis, that introduces certain correlation, but this was incomplete answer. So here you can see in a more complete way what is the scenario. But again, these are something that goes in the data analysis, and yeah, I just want to give you a glimpse of that. So for example, mu b is what we are trying to calculate, right? So this has several correction factor. For example, this alpha x1 is the decline rate, and c is, I think, color correction, and then alpha and beta are the nuisance parameters. So they've had this x1 and c vary for different supernova, and they are provided in a table. But this is not what we are doing with union 2.1. Okay, so understand the difference. This is what I'm talking about, this paper where union 2 data sets or union 2 analysis was released. This union 2 compilation. Cosmology is compared with the nuisance parameter alpha and beta variation. Cosmology is compared with the data. So this is the data which has alpha and beta nuisance parameters. So this likelihood embeds this variation of alpha and beta, and mu, where this is the theoretical mu. Okay, distance modulus, which depends on, let's say, omega matter, w and omega w. Okay, so if you are saying your omega k is not 0, it is omega w, then this sums over all the supernova. As you can see, this is simply the simple chi-square that I termed in my notebook. And here, this sigma light curve square is the error bar variance obtained from each of the supernovae, and this V is the covariance matrix from the light curve fits that are light curve fits for individual supernova. So as you can understand, when you do the light curve fits, individual supernova has a covariance matrix. Now, So you can see that here we are not talking about any covariance here. But what happened is that in Union 2.1, they changed the analysis. What they did is that they ran the supernova with alpha and beta parameter, carrying systematic errors that has calibration, galactic extinction, etc. There are lots of astrophysical processes that are involved, lensing. Although I'm not sure if lensing is termed as a systematic error, but it is taken into account. So there are many systematic errors which you can find in this paper, and uh, they are varied alongside cosmological parameter. Now, if you minimize over this nuisance parameter, this gives additional contribution to the distance modulus covariance matrix. This you can find in Suzuki et al. 2011. Sorry. For cosmological constraints, therefore, in order to not invert the covariance matrix every time, what they do is that they actually determine this UI, this distance modulus covariance matrix, using this, and epsilon are basically the different systematic errors. Okay, so epsilon goes from 1 to 2. For example, if it is 1, I mean, we are talking about calibration, then other effects like galactic extinction, etc. But then once you obtain the full covariance matrix, now as I said, this is under the one umbrella. Okay, all the supernova comes under one umbrella, and then alpha and beta are actually minimized, okay, for the whole supernova, which basically brings a correlation when you bring them, when you basically minimize the whole data using this alpha and beta parameter and the cosmological parameter. So this gives additional contribution to the distance modulus covariance matrix. So therefore, this off diagonal ij terms gets populated. And for cosmological constraints, what we did and what all people did with supernova 2.1 is they had this fixed covariance matrix. They inverted the covariance matrix, and just as I showed in the notebook, they used the fixed covariance matrix for the analysis of the cosmological models. Okay, so therefore that's why this effects of alpha and beta comes inside this all the systematic error effect comes inside this off diagonal terms of the covariance matrix, and also in the diagonal terms in some extent. Okay, so does it answer the question whoever has asked me?
Yes. Okay. So this comes when we are trying to purify the raw data set, some kind of, so scaling those things and averaging those things.
Exactly. So there are mutual calibration. Let's say in one of the, let's say there are 10 data sets, right? I showed different data sets with different colors. So there are, let's say, 10 data sets, and each data set has their own calibration. But now you have to do this. You have to marginalize over all these calibration parameters, right? We discussed also in the Planck analysis in the CMB that we have not four frequency channels. We have 3 frequency channels, 100 gigahertz, 140, and 217, from which we get 4 auto and cross spectra: 100 cross 100, 100 cross 143 cross 143, 217 cross 217, and 143 cross 217. So each of the spectra, when you are allowing your cosmological parameters to vary, you are getting the CLs, and while matching it with the data, you are also allowing a mutual calibration factor, for the I mean 3 of the spectra. You are allowing them to vary, so that you are saying that this is the relative calibration between frequencies, and there is another overall calibration as well, so that you are multiplying the whole data. So that is how you are marginalizing over all the systematic effects in Planck. So here, instead, you see what we are doing is that we are doing this calibration earlier, and let's say you get a co-added data from Planck. Then you say that, okay, I have already marginalized my calibration there. Now Planck data is not, Planck data, you don't have to take individual calibration. I have a single data, not 4 data sets. Now I have just a single covariance matrix, and then I can do the analysis. Here, this is what is happening. That here you do this alpha and beta with for different X1 and C and MB for different supernovae. You minimize them, and in the whole data, when you are doing the analysis afterwards, then you basically get the full covariance matrix that has the systematic errors included inside.
Okay, sir. Okay.
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 But one thing I noticed that these references are not very difficult to understand. Of course, you have to understand a little bit about this light curve fitting, but you can go through these data sets actually. So it is a good, these two papers are good read. You can just have a look at those papers at some point of time. Okay, so it is also good to understand the data analysis part, how things are done. So for example, you can understand, if you say that, okay, I'm just varying omega matter and omega w and getting the constraints, but if you understand the underlying physics of this data, that is even more interesting. So yeah, I would urge you to go through that course. Okay, now we discussed all these distance measures. Now what modification we need in order to change this distance measures, right? So what we assumed in the last few lectures, the dark energy equation of state is W equal to -1, but it is different from cosmological constant, which is W equal to -1. If it is different, then it changes the distance measure compared to the standard lambda CDM model. Then you have to use this relation P equal to WC square rho. Okay, so when we say P equal to W rho, you know that we assume C square equal to C equal to 1, and rho dot is 3h rho plus P by C square. Okay, so these are the equation of state and the fluid equation, and then if you solve it, you will find that rho is equal to exponential of -3 integral of 1 plus W d log A, where W is the equation of state. Okay. So now it comes to the parameterization, that we do not know this W. Okay. How you can know this W? First of all, if you just say that I am doing a phenomenological approach. Okay. Phenomenological approach is something where you simply parameterize that W of Z. You say that I do not know this W of Z, so let me parameterize with certain types of, let's say I Taylor expand, or I give as from the data, let's say from I have some certain hints, and I say that okay, we need this much change in the equation of state around this redshift. So let me add that as a correction term, or as a, I mean, possible theoretical term, without having an underlying theoretical support. Not always, it doesn't happen always. So but you say that okay, let's say I am assuming W equal to -1, but at some point of time or some redshift, the data seems to suggest that there is a redshift region where you need your W that goes less than -1 or greater than -1. In those cases, you say that okay, I am adding a step function which says that it is -1 before, and then it becomes -2 or -0.5, depending on what the data you need, and then you compare that with the data. Okay, so this is a parameterization. So you can do two types of parameterization. There can be many others, but I have explored two of them, and two of them are really popular. So I'm going to discuss these two. So one is the parameterizing the equation of state W of Z, and parameterizing the dark energy density. Okay, rho dark energy. And then the third one is that you can have a model, a proper theoretical model to describe the dark energy. So this is the quintessence model. Okay, so where you can have a scalar field model just like the inflation model. Remember, we had a model, a scalar field model, and we basically said that the inflation in the scalar field goes slowly down to the bottom of the potential. That gives an accelerated or exponential expansion of the universe. Similarly, here we can see that. And most famous parameterization, which is the baseline. Okay, baseline is without W equal to -1, which is the most standard parameterization that are used in any dark energy analysis, be it Planck, be it supernova, etc., be it baryon acoustic oscillations. That parameterization is called Chevalier polar cylinder parameterization. The two references are there. The first one is by Chevalier and Polarski, and the third one was by Eric Linder. And this is parameterized as WA, and which is written as W0 plus WA times 1 minus A. sometimes the WA is assumed to be 0, and it is assumed that, okay, let us assume that W0 is a constant, but we are allowing this constant parameter to vary. So constant over time, but it is we are allowing it to vary in our analysis, and we are trying to find whether our W is actually -1 or not. So we did this analysis. One important thing that you can notice here in this from this paper is that your course coordinator, Professor Supratik Pal, and two of the instructors, Professor Anjananda Sen and me, are part of this paper. So you see that this was the I would urge you to have a look at this paper, because this is one of the earliest, or I think one of the first few papers that came after Planck 2013 data. So this was one of the first analysis, and that includes a lot of models, etc., model analysis with different data sets, and we show the tension and agreement between different data sets. So this is a pretty good model analysis paper, I would say. So I would urge you to go and have a look at this paper. Okay, so what you see that W equal to -1 is this line, and this is with Planck and various other data sets. We are getting this 1 sigma and 2 sigma constraints, and it is showing that, okay, W equal to -1 is rejected by 1 sigma, or it is just 1 sigma out. So it is called marginal rejection, or not worth mention rejection kind of thing. But still we found that there are certain hints of phantom dark energy. Phantom dark energy is the case where W is less than -1, and it is supporting that at up to 0.1 redshift, the Planck data prefers W equal to -1. And if you remember the Planck analysis that I showed you, W0 and WA, there also we did find that this W0 WA, so that is the Planck 2018 analysis I showed. The plot from the from the Planck 2018 paper. If you add temperature and polarization since 2015, you would see that actually W equal to -1 is rejected at 2 sigma or close to 3 sigma. Okay, and this is the posterior timeline or posterior band on the evolution of W of Z based on our analysis on WA parameter. Okay, now if your theory says, let's say that we have certain underlying theory that prohibits us to have a W less than -1, in that case you have to use a prior cut. Prior cut is a theoretical boundary where you are restricting your model, and you are saying that your model should not cross this -1 limit. Okay, in that case, what you can get is that from the here you can see that your W can go, yeah, W0 is here at redshift 0. Your W0 can go up to -0.7 or something like that, -0.7. So if you use certain types of other parameterization, for example, Chaplygin gas equation of state, you can have a look at these papers. Okay, I am not an expert of these models, how these models actually come, etc. And this paper is another paper. So Professor Anjananda Sen is expert of this, an expert of this paper, because he has indeed worked a lot, or I think introduced one of this model in Bento et al. And there was another model by Sherar and Sen paper that I'm going to show you, but that is related to the directly related to the scalar field evolution. Okay, so if you say that my dark energy is not allowed to go to an equation of state W equal to -1, go beyond the go in the phantom region, then you can see that the Planck data along with the other data sets. So whenever I say Planck data, remember Planck cannot constrain the dark energy. Okay, dark energy equation of state. Okay, Planck alone cannot do that. Planck has a degeneracy with H0, so we cannot actually constrain any of the parameters of W. So given if you allow H0 prior to go higher and lower, your W can become higher and lower. Okay, so it is just the fact that you are talking about the distance to the last scattering surface, and we are going to show something that you can also do it at home by changing W and H naught and see what is the effect. Okay, so this is the main point, is that not only Planck but with all other data sets we find that at W equal to -1 we do not get any constraint. Okay, so the contour is open here. So it is consistent with 1 sigma. This is the best fit. And we have an upper limit of W saying that it cannot be more than 0.8 minus 0.87. Remember that it is a little bit stronger. So this is an important thing about the constraints I would like to mention. If your, so here you can see that it is minus 0.87 at 2 sigma, but here it is minus 0.7. Okay, so here we are getting tighter constraints. You know why? Okay, anyway, we are getting tighter constraints because here we have more flexibility. For example, the data is happy to be phantom and go up to minus 0.7. Okay, so that actually compensates. So if there is any change in the distance to the last scattering surface, because your dark energy becomes phantom, it can be compensated by the change in the distance module, your distance by the owing to the change in the W0, which is up to 0.7, minus 0.7. All right. So here we have less flexibility. So the model is constrained more, but it does not mean that today actually W is constrained to be minus 0.87. Okay, so these constraints are dependent on model. That is why whenever you do an analysis, your analysis are your analysis are almost all of the time are model dependent. Okay, your results are almost all of the time model dependent unless your model has enough freedom. Okay, so this is a lesson that you will understand if you just run this model. That is why I would urge you to have a look at this paper. And there are many other papers afterwards as well, and before that with WMAP. But Planck analysis with new data sets had a really good grip on the dark energy equation of state. Okay, so this model can be parameterized as the rho p equal to minus c by rho to the alpha. The equation of state from there can be obtained like this. Okay, and here what you do is that you can change this WA inside Planck's equation inside CAM's equation .f90. The recent version has changed. I think now the recent place where you need to change is dark energy .f90 or something like that. But earlier, at least 2 years or 1 year earlier, it was named as maybe 2 years. Okay, so it was named as equations or equation underscore ppf.f90. Now the decaying dark energy. Okay, so decaying dark energy is something that we had worked on in this paper, and I'm just showing two of the models that we have used. So actually used 3 models. One is where the dark energy decays to itself. So the dark energy, let's say, having an equation of state of W, but it decays to itself with a changed equation of state. But here the dark energy, I have a decay like this, and this decay is added to the dark matter density. Okay, so this is a coupled differential equation that you need to solve with the help of the Friedman equation 3h square by d by g. Okay, you need to solve that, and then you get the full evolution. You here W equal to -1, here also W equal to -1. So here dark energy is decaying into dark radiation. Okay, and then so dark radiation are the relativistic species that are beyond that are not photons. Okay, and or neutrinos. Okay, so these are extra relativistic species that we are talking about. Okay, and yeah, and then check. So the solution of h of z, remember I discussed that h of a small h of z is basically hz, capital Hz divided by h naught. Okay, so there is a factor gamma. Okay, and if you change this gamma factor, then for different omega matter, you can see if you change this gamma factor, how your h changes for different. Now I'm changing omega matter. Now I'm changing, you see, the different types of decay. So let's say gamma equal to minus 500, and I'm changing omega matter. See the top panel. Now I'm changing gamma dark energy. Okay, let's have a look again. So when you do the analysis, you are allowing all of them to vary. So W of Z, how W of Z looks like, if you change omega matter, nothing changes, but gamma. So this is the one where the decaying dark energy is decaying to itself. Okay, but for the other cases, W is assumed to be -1, and this is another one, the Q of Z. In all the cases, you can see. Okay, notice if gamma is positive, then that means what it means is that gamma is basically your dark energy is decaying to dark matter more. So if it is highly positive, that means that you are basically decaying to dark matter. So if you're producing huge amount of dark matter, what it means is that you do not have a dark energy to accelerate the universe at the present time. So you can simply see from the plot, right? And if gamma is negative, that means that you are getting more dark energy density. So you can see in this case where it is frozen at gamma d of 272 here in this particular box, which is positive gamma. In this case, your Q is always positive. That means universe never was accelerating. Okay, definitely you can understand that if you do this analysis, this type of high positive gamma is going to be ruled out. All right, so have a look, and if gamma is negative, then you have very sharp drop in Q. That means it is, yeah, see, it is therefore accelerating. Have a look again. Okay. Now, before we go to the quintessence model, let us do certain analysis in that. Notebook. Okay. I think I should write it too. Are you able to access this one and run it in your own Psi server? Let's have 30
Yes.
seconds. Okay, good.
Yes.
Okay, others, please, if there are anyone who is not able to run this, please type here.
Import MNs not running. Import MNs.
Import
MNs.
where?
EMs.
Where?
TIHISI 4 lab.
No.
Notebooks.
I'm saying which cell, for example, or where you are. Can you write which one is not working? Please write it. Type it in the chat box.
Okay. Okay.
It is in the notebook folder. Yesterday's notebook folder. That I mean, we have been using the same notebook folder. You just copy this one. TIH4. Yes, see this one. Dhiraj notebooks. TIH4DE2. And yeah, which one was not working? Please type it here. The exact error message. Import MC. So it is the MCMC code. You have to install MCMC. Yeah, this one. Just type in and install that. But I assume that yesterday when we explored this, MC you had installed in your directory, right? Partha?
Yes, sir.
But okay. Anyone else having any problem with this, with opening or copying or running this? I'm not asking you to run everything right now. Okay, so let's take one step at a time. Okay, I am assuming that you are all set. So here we provide the references in each section when we proceed. Okay, when we go to this section, you will be able to see this. Okay, and these are the Friedman equations. AZ, CPL parameterization. W, I am defining W here. W0 plus 1 minus a WA. Define omega dark energy from here. Omega dark energy is 0 today times exponential of 3. The one that I had written in terms of A, it is written in Z, or in terms of A, it is written like this. Omega dark energy at any time, but the scale factor A was equal to A, is the omega dark energy today times exponential this integral from 1 till that date. And this one is defined in the EOS integrand, you see. So W is basically WA W0, which I am just calling from there. Okay, here W now is means W at A. Okay, W now doesn't mean W equal to W0. So you are getting the equation of state, and omega DE can be obtained from this equation of state. Omega DE like this, you see. And the integration should be in log A. You see here, if I ask you to integrate and get me the omega D at any A, I am basically computing it from log A equal to 1 and log A. So this means 0 to some log A. Now combing distance, definitely you will, the thing is that you will have to change the arguments, because now these are functions of these parameters, or also you can write like an object-oriented programming. You can code it in like an object-oriented fashion, and then you can just pass the arguments as you wish. So moving distance, DH, the horizon, angular diameter distance, everything is calculated. Luminosity distance, distance modulus here. Just like yesterday, we plotted the distance modulus here. Before going to the quintessence model, let's just check.
Excuse me, sir.
Yes.
So I have a small doubt that angular diameter distance and co-moving distance in
Yeah.
curved space also related by that same relation, right?
it will include this r divided by 1 plus z times sine of the moving distance times the divided by
co-moving distance will change.
yeah sorry, it should be it should include this square root of omega k. I have the exact expression, you can find it in my first lecture where I have provided it. Okay.
Yes, sir, I saw that. My doubt is that angular diameter distance changes the relation between angular diameter distance and the co-moving distance. Is it the same, or co-moving distance changes according to curve?
This is for the flat one. It will change if you use the flat. If you use the use it for the curved space. Okay.
Yes, sir. For curved space, co-moving distance will be will change, right?
Yes, but
co-moving
okay,
distance.
one thing is that the luminosity distance and the angular diameter distance, this is going to be this relation is going to be the same. Okay, so dl should be dA divided by a square z. Okay, so you can also write it as angular diameter distance times divided by a square z.
Yes. Okay, sir.
So there I have listed a few assignments where you need to make these changes and do this calculation. Okay. Yeah. Any other question? You said you were saying something.
Yes, sir. I plotted that distance modulus versus redshift for the curved space, and I got the exactly same plot for k equal to -1 and k equal to +1. It was different from that k equal to 0. Distance modulus decrease initially, like the value was decreased, but shape was similar, like the same shape.
Have you
as the k equal to 0, but the value of the
okay.
Yes,
have you checked have you taken the sine and sine hyperbolic factors
yes,
in
sir, yes, sir.
account accurately and
Yes, sir. I used the slide lecture expressions
okay and
from
okay,
the first lecture.
let me give you one link how here. So there is this cosmology calculator, a very famous cosmology calculator that we have been using since our PhD days, Ned Wright's cosmological calculator. So you can give the values here and check what is the moving radial distance or angular diameter distance or luminosity distance for different cases. For example, you can use open universe or flat universe. You can check that, and I think there you will be able to also find advanced cosmology calculator, this one, which has a little bit more input. Yeah, that is fine. Potential risk in the link. This website might be trying to steal your no Ned Wright is not stealing your personal information. Make sure the URL is valid and copy paste the link below to continue this site. Now this is something that we have been using for a long time. So I believe, okay, so this is okay, I believe that there are no risks, but I cannot guarantee it because it is showing and showing certain warning, and I should not override what Firefox is saying. So yeah, on record I cannot say that you should try, but usually it is not harmful. We have used it as I said from our MSc PhD days.
Thank you, sir.
This is not a secure site. That is why we are getting these problems. Let me check if there are others. Yeah, these are different other lists as well. This should be a secure one. Okay. And but if you click on those, I think it is taking you to a insecure website. Okay, this is going for the Fermilab, etc. But yeah, but anyway. Yeah. Now, this decaying dark energy. So let's just take the dark energy decay as this. The dark energy have a radioactive like decay with the gamma is related to the half-life. Okay. So rho dark energy T is rho dark energy T0 times gamma times exponential gamma T minus T0. So it is simply described here, and you can write an autonomous set of equations where you can write this differential equation. Okay, this one, and differential equation of dH dt or dH dz, and you can simply solve that differential equation and get the plots, get the evolution of Hubble parameter, evolution of dark energy equation of state. As you can see here, it increases, WZ increases over time. And yeah, you see, I'm taking the solution of this decaying dark energy by this ODE solver using this initial condition HIC. It just depends on the this small h, and you write everything in terms of gamma by h naught. So you g by h. So you are parameterizing this gamma with by making a transformation. Gamma goes to gamma by h naught, where you're taking the present Hubble parameter out of that equation. And from there, you can simply solve for h of z. As you can see, it is giving you dHgz, right? So given, so this is first order differential equation. So when you solve that, you just need you just need a initial condition, and you can simply get the full evolution. Okay? Here I am plotting the full evolution, and okay, this should be W of z. And with respect to that, you can simply write the W of z. This is the expression for W of z in this uh, uh, in this particular parameterization. And Q of z, as you can see, is the evolution of the deceleration parameter. If it is -1, you remember it was reaching to -0.5, but here we are having a slow down of acceleration, so it is reaching up to -0.4, or it is the acceleration is not as much as the lambda CDM case. That is because of the fact that W grows higher than -1. So what I would urge you to do is that here I'm coming to the GCG model itself. Okay, yeah, GCG model I discussed, right? You get the distance modulus as a function of parameter alpha. Get the distance modulus for the decaying model. So you can either look at our paper, or you can here for the GCG model, you can look at the original papers that I have referenced. Okay, and get the distance modulus for the decaying model I mentioned. Get the deceleration parameter for different. Okay, this is related to the quintessence that I haven't covered yet. But let us go to the comparison of the model of of the CPL model with the data. So again, I'm not going to the details because I already discussed this part. Again, this one needs to be changed. So this is not zero dark energy. This is theoretical prediction. Okay, I think this is something that I'm using from the best fits. Yeah. Okay. So yeah, definition of goodness is of it is the same. Cove mat is there, and it is the inverted cove mat already. And now you see what I am doing is that I am basically asking it to give me the chi-square for these values, W0 baseline value of Planck and WA baseline value. Sorry, W0 base and WA base. Let me just have a look. Okay, it is not written here. Sorry. Let me go to the place where I had defined W0 and W1 baseline. Yeah, so W0 base is -1 and WA base is 0. That means I'm using lambda CDM. So for lambda CDM, the best fit, as you can see, is 545 chi-square. Okay, for this 580 supernova data. Now, oh, okay. So supernova chi-square, you can simply now solve for it. Try to find the best fit chi-square by allowing these parameters to vary, the W0 and WA to vary alongside omega matter. And it is taking a little bit of time, but yeah, it is there. So as you can see, we have been able to solve it. So it has point. It is saying that we have 0.29 or 29% of matter, and you can see that it is consistent with W of -1. It is the best fit is W of W0 equal to -1, and WA is 1.6 times 10 power -4. So it is completely consistent with the lambda CDM. Okay. So this is another thing that I would like to mention. So I do not want to criticize I mean, I do not want to criticize the single covariance matrix analysis of supernova, but sometimes, I mean, earlier supernova data, I think Union 2 or before that, when they use the when they marginalized over all the correlation matrices alongside this varied parameters, then I think it was in some paper by Arman Shafilu et al. They showed that the recent acceleration is slowing down. So we are still accelerating, but there is a slowdown of acceleration if you allow a little bit extra freedom in the parameter space. But when Union 2.1 came, it went away because of different scaling or calibration in the data. So you have to understand this type of calibration if you want to dig deeper. Okay. So this one, I just wanted to mention that sometimes analysis, I mean, I do not know which one is the correct analysis, but usually the higher versions are supposed to be better than the lower version. So lower version release of the data. But this you have to keep in mind when you are doing this analysis. Okay. Now, yeah. You can simply plot it. It should not be any different than the lambda CDM best fit. As you can see that it is we are getting the best fit is exactly same as the lambda CDM. So 10 power -4 is negligible, right? So you can also, I mean, in this case, you can plot the deceleration parameter. Okay. So Markov chain Monte Carlo, you can do it at home. And what we are varying here, so we have understood that with the covariance matrix we cannot constrain H0, right? So that is well understood, I believe. So now we have three parameters. You can simply put H0 to take whatever value, and then you just run for the omega matter, W0 and WA. So you are varying three parameters here, 100 Walkers and 500 iterations. It takes about how much? It took about 2 hours of time, I think. Yeah, 14.69. Yeah, and if you do it in Cosmo MC, it will take 10 to 15 seconds. Perhaps a bit more if there are degeneracies, but anyway, but these are good to have. These tools are good to have because you can simply understand from the codes. This notebook gives you a way, right? So you do the smart curves in Monte Carlo, and after that you post process that, okay, using corner. And what you see is that your omega matter, if you allow these parameters to vary, your omega matter equal to 0 now is not ruled out strongly. Okay, if you compare with the old analysis here, where we have been using W equal to -1. I think it should be here as well. Don't worry. Here you can see omega matter equal to 0 was completely ruled out by the data. Okay, anyway, so I think here one more thing is that it is 0.15 here. So this is 0 point. Okay, so W omega matter equal to 0. But here I think the minimum value was 0.1 if I'm not wrong. So you can see even 0.24 is 0.32, so that means 0.16. This is 0.16. Okay, so it is increasing by 0.08. So this point is omega matter equal to 0.16. You see that if you allow your omega matter, I mean, if you allow your dark energy to have a fixed equation of state, that is the lambda CDM, then you can get a complete constraint or two-tailed constraints on omega matter. But if it is not true, then there is a huge correlation. You can see that this ellipses are correlated. These are tilted ellipse. So this omega matter is correlated with W0 and WA. So you can still fit the data to a very good extent if you allow W0 and WA to change and also keep omega matter to 0. But again, you can see that here it is 0.45 and this is 0.6 then. Okay, increment is 0.15. So this one is 0.6. It is not saying that the data is happy. The analysis is not saying that the data is happy with omega lambda equal to 0. So omega matter equal to 1 is ruled out, but omega matter equal to 0 is not. That means that the supernova data says that it definitely needs a dark energy. You can see the example later on as well. Get the bounds and parameters just like before. Plot the samples of mu. Okay, these are the data points, and these are the mu samples randomly selected. 100 mu samples, 100 or few of them. I forgot how many I'm plotting. Randomly plotted from there, and here I'm plotting the samples of deceleration parameter. So there in the last one, where we did the analysis for lambda CDM, we had seen that the deceleration parameter has a unidirectional or monotonically decreasing value. All right, here it is monotonically decreasing up to certain value because of the radiation and matter. So there is you are not able to change that. But then it can change because of the change in the equation of state of dark energy. So here everything converges to -0.5, but here it is not. You can see that it is still here. These are the lines from the samples. Okay, here you see that it is still consistent with the zero acceleration of the universe, zero acceleration or deceleration. Can anyone say that whether this is saying that we are happy with no acceleration of the universe from the plot? Can you say that? Can anyone unmute and say what this plot implies?
No, sir. At redshift 0, it's showing that the acceleration is minus 0. Around 0.5. And so it's increasing. You can say it's accelerating.
This is a very good answer. Yes. So that means that at some point of time in the recent epoch, the universe must be decelerating. Okay. So you see that the data, for example, this sample, this is showing a tremendous acceleration. But in order to compensate that, it must be decelerating faster. So that means that it has the acceleration started late, and that is why it has to accelerate much more in order to make the distance modulus happy from the supernova data. Here, it is not accelerating now, but it was accelerating during the cosmological constant dominated epoch. So therefore, what you are seeing that there is a very gradual change in the slope afterwards. Okay, afterwards means that when you go back in time. Okay, after what you say backwards, yeah. If when you go back in time, the equation of state that you can simply sample. Okay, and this one is the best fit. Yes. Let me check. This is the best fit or the red one. Color K red. Yeah, this is the best fit. What I'm plotting here is the best fit, the red one. And this one, you know, the best fit came out to be just the lambda CDM, right? Lambda CDM value. So the best fit is simply the red line, which is simply lambda. And these are the different samples of the W of Z. So these W's of Z gives you this Q of Z. Okay. So the distance modulus data is happy either with W of Z greater than 0, but a very visible change of W of Z in the recent times, or W of Z less than -1, sorry, W of Z greater than -1 for a long time, but then a very visible change in W of Z in the recent epoch, or W of 0 phantom all the way, and presently it is increasing towards W of Z greater than -1. Okay, I hope that you're able to follow. Now let me go to the quintessence model. Okay, so canonical scalar field that describes the late time acceleration of the universe is known as quintessence model. Remember that this model in a standard gravity cannot give any equation of state of W which is less than -1. So phantom dark energy is not achievable in this type of Lagrangian. So you need to change the Lagrangian. You have to go to the modified gravity of Lagrangians. I mean, you have to modify this Lagrangian, and then you can achieve this W less than -1. Simply the equation of state in the we discussed it, right? The P of phi, the stress energy tensor, is basically this T mu nu is showing the P is phi dot square by 2 minus V of phi with a factor of square root of 8 pi j by 3, and then rho of phi is phi dot square by 2 plus V of phi. So if the scalar fields roll slowly, then very slowly, you can neglect this phi dot square term, right? Phi dot of square term with respect to the potential. If the evolution is potential dominated, then this you make this 0, and then you say V equal to, and then you cancel V from the numerator and denominator, and then you find W equal to -1. Okay, but in any other cases, this changes. Okay, so there is a evolution. W changes with time or field values. The scalar field satisfies Klein-Gordon equation. I hope that you remember this one from the inflation topic, inflation discussion. You simply get the Friedman equations, but there you can also solve simply from the phi I. But there people uses now a different set of solutions by changing the equations by certain reparameterization. You can have a look at this paper by Professor Scherer and Professor Sen, and this review by Professor Shinji Sujikawa. Okay, here you define x as the velocity of the field, y as the potential divided by 3h square, and lambda is defined as 1 over v d by d phi. Okay, so it is like a slow roll parameter kind of thing, but it is there it is v phi by v whole square, right? So omega phi you simply can be obtained by x square plus y square. You take that x square plus y square. So this is phi prime. So you can simply see that it is coming out to be rho phi, right? Rho phi is phi dot square by 2 plus v. So this turns out to be x square plus y square. This and gamma equal to 1 plus w is written as twice x square by x square plus y square. Then in terms of x, y, and gamma, the equations of the scalar fields and the Friedman equation can be written in terms of this. All right, these are the equation that we are going to solve. Now, the scalar field model with a power law potential, there are further simplification, that this gamma equal to v phi d2 v phi, this d2 v d phi 2 divided by dv d phi whole square. So you can also write this gamma prime omega phi prime, how much your scalar field density changes with time, so you remember, you understand that this scalar field density here, but we are talking about a scalar field density is indeed the density of the dark energy, so omega dark energy, right? And this is the lambda equation for lambda. So you need to solve this coupled equation. As you can see, these are the coupled equation that you have. So gamma is coupled with gamma, and omega phi is coupled with lambda prime equation, and gamma is coming here in the omega phi equation, and this gamma prime has both omega phi and lambda. So there are the power law potential. If I take a potential with phi to the -2, then you can solve this for gamma, and the evolution of omega phi is this. So log A, 0 means today, and this is the early universe. Okay, so now at this type of model is saying that it is this omega phi is nearly constant up to some point, and then it picks up. Okay, power law potential with n equal to +2 shows a different scenario here, that okay, I am okay -2, okay, but here I am plotting w of z instead of rho. So you can see in these cases w equal to -1 up to certain redshift or certain scale factor, then it starts increasing. Okay, there are different types of models, tracking freezing model and then scaling freezing model. I am just going to discuss two of them. I always mix these names. Okay, so apologies if I'm not too good with names. Tracking freezing models, you can also have a look at this Sujika review, have this type of power law potential that I just discussed. It has initial slow roll and later approaches w equal to -1. Okay, so this is A when it is the A equal to 0 big bang, and then it slowly approaches. It is initially different from w equal to -1, but then actually it comes down to 1. And this has one particular property why it is called tracking is that it has, so matter and this dark energy follows a common evolutionary track, or the dark energy tracks the matter evolution. So that means the dark energy tracks the omega matter. Okay, so if you see the review, you will find this. You will find the plot of omega matter and omega phi. You will see that it is tracking the matter. So they have a common evolutionary track. That is why the tracking name came. And thawing model is coming from this type of potential, pseudo Nambu-Goldstone boson. So this field stays nearly frozen at early epoch. So that means that this W equal to -1, but then starts evolving afterwards. So this is thaws. So that's frozen state thaws, and then you get W is greater than -1. But in none of the scenarios, as you can appreciate, that W is less than -1. Okay, either W was greater than -1 comes to -1, or W was -1 and goes greater than -1 as we go forward in time. So these are again the assignments that I had written. So you get the deceleration parameter for different n values ranging from positive to negative values and solve for 2 other models of decaying dark energy. Okay, that I had the reference I had already given. So for this one, it is very easy. You change the n and you just see what the initial condition that you have to change. So there is, I mean, you can understand when you run this model, if you change the potential, how it is changed. For the 2 other models, you can see our paper. This is Safilu Hajra Sahanis Taravinsky, 2018, I think, MN RAS. And in that case, you have to solve for 2 other states where basically dark energy decays to dark matter and dark energy decays to dark radiation. This is something that I had already discussed. Let's go back to the notebook. Yeah. So scalar field model of dark energy with a power law potential, you can write it like this, where this is the definition of gamma. So if it is power law, then gamma is simply a number. Okay, this gamma is simply a number. This is power. N power is the power. It is phi to the n. N power minus 1 divided by n power. So these are the equations. Remember, gamma prime. This is d gamma. Omega phi prime, d omega phi, and lambda prime, d lambda. Okay. So these are just simple equations that you need to solve. Using certain initial condition, you are starting from 10 power minus 3 when log A is 10 power minus 3. And you are going to, log A is minus 3 and log A maximum is, okay, so this is natural log, sorry. So it is exponential of minus 3. A is exponential of minus 3. So, and this is today. I'm solving from an early time till today in 500 steps. And I'm giving this initial conditions and evolving this. And the solution is obtained as this using this initial conditions. And you can see this is the evolution of gamma. Just check if you are able to run this and these run and solve for these omega phi's or the gamma. Okay, just check if you are able to solve this. Write yes in that chat box. Can you check by changing this power? Let me do that. You see the gamma, the value up to which it reaches log A. Sorry, just a second. Okay, now we just plot it, and omega phi, which is up to -0.8, and then solving. Yeah, so you see that the value of W up to which it goes, it changes, and also this lambda and omega phi changes. Omega phi is omega dark energy. This is saying we have 85% of dark energy today. Okay, and okay, in the chat box, everybody is saying yes. At least I got 7 replies that says yes. Okay. Okay, I keep on forgetting always. So this is something that was troubling me. So NP log is 10 power minus 3. I forgot in Python it is log 10 or log base E when you write a log. Okay, so that is why I'm not able to completely make sure that it is log A or LNA. Okay, somebody said something. Base E. Okay, so I can just check here, right? Okay, this is base E. This is natural logarithm. Okay, fine then. Okay, so what we are doing is that we are going from 10 power minus 3 to 1. So I got confused in this step because I did not remember. But anyway, 10 power minus 3 in natural logarithm is e power minus 7, I guess, right? So anyway, then your job is to check the other one, right? So in power, I had already given for up to 2 to 4. You see that it is working. You have to go to the negative power and check what is happening, and you try to understand the differences between these solutions. Okay, differences between these solutions, that what is for the positive power and what is for the negative power. So everybody is fine with these solutions? Please write back. Should I proceed now or? Okay, so I guess it seems trivial, but one thing I would like to mention that it just this shift enter and everything, so it might seem trivial. So definitely it is really important for you in order to understand this subject fully. It is really important just not to rely on by changing this power. Okay, so if you change the power, you will understand that there will be some problem in solving this. So you need to change certain other things. Okay, I'm not saying what other things, but not the equations. Of course, equations will be the same, so you can understand what certain other things I'm talking about. Then you will be able to understand those parts. But it is really important to uh, dig deeper in this subject. So you survey the literature and try to see how other differential equations are solved for this quintessence model. So what this notebook is giving you is a platform to solve the models. It can be W parameterization, it can be rho dark energy parameterization, it can be a theoretical model. You can simply solve it and then put these back inside the distance calculation and then constrain these models. Okay, so this is something that this notebook provides. So you do not, this saves you a lot of trouble on the analysis, but it is always advisable that you write your own code. And even if you use this code, you try to understand this as much as possible. For example, I said that check these, right? Check these as assignments. Where were the assignments? Sorry. Yeah. You can now you have a dark energy parameterization from the theoretical model. So and also this parameterization, I showed you the constraint from W0 WA. What you can do is that you can simply take this GCG model, get the constraint. You can simply take the rho dark energy model, decaying to itself, or rho dark matter, and then get the constraints, or you can use the quintessence model and get the constraints. There, in every step, you will solve this differential equation and you will vary this parameter, and then you will be able to, there are parameter n and other parameters. If you are able to find, then you get the constraints on those parameters instead of just parameters in W0 WA. Okay, so now let us concentrate on another part. So I discussed this baryon acoustic oscillations, right, in the blank CMB. Let me show you a schematic animation prepared by Bruce Bassett, Rene Lozek, and Daniel Eisenstein. Here you can find it in any, just search BAO animation and you will be able to find it in the as a GIF in any of the if you Google it. Okay, so this is showing the evolution, okay, showing the mass profile of the perturbation in the real space in megaparsec. And remember, I said this baryon acoustic oscillation has a characteristic peak at 150 megaparsec inverse. That means if you take compass and take circles, make circles in the sky of different uh, diameters, okay, or radius or diameter, you will see the at 150 megaparsec. If your compass length is 150 megaparsec, you have more number of galaxies compared to other places. Okay, of course the correlation will be picked at 0, but then you will see that there is a particular peak when it is going down. So when it is going down, then up to 100 megaparsec, then there is a peak at 150 megaparsec before it falls down again. So what is happening, you see gas and photon are given in red and blue colors. They are moving together over time, and this animation is over time, right? So you see this is Z is decreasing. That means we are coming today Z equal to 10, but we are starting from a very early period of the universe. Just see when it starts, 20,000 or 40,000 we are starting, then 17,000, 13,000, then photon decouples. So what happens is that photon and baryon were interacting together strongly, photon, baryon, plasma. So then I'm giving you another scenario. As I said, that the gravitational wave, gravitational potential pulls everything together, the photon, baryon, dark matter, etc. But there was pressure, outward pressure, because of the photon baryon interactions. So which was giving an outward pressure. So they were going apart, and then there was again, they were coming to the potential again, the minimum of the potential again, and then again they were falling apart. So that is how these oscillations came into the picture. At till certain point of time, it was working, but after that, when the photon started decoupling from matter, they left those matter at those places, and the overdensity were frozen at 150 megaparsec in 150 megaparsec inverse. Then after that, dark matter was not interacting till the late time, okay, because dark matter never interacts with photon or baryons, okay, the normal. So as you can see that it was always constant, it was just falling on the over density, it was just falling on top, neutrino was freezing away, but this dark matter was falling in the over density. But then see what happens, then dark matter tracks this baryon, tracks this matter. Why? Because you see this decoupling happens, baryons gets frozen, then the baryons drags this dark matter using gravitational potential, because dark matter interacts with gravity, then everybody interacts with gravity. So it is actually bringing the dark matter together, and then wherever, if we when we say that these are the over density so of matter, now when we talk about over density of matter at a particular place, is also implies that this is all, there is also a dark matter over density, because when photon decoupled, then the baryons simply baryons and dark matter attracted each other and they formed this halos. Okay, so I think you have already had discussion on halo formation. Okay, so the phase one, this is the biophysics in different phases. You start with three species: baryon, dark matter, and radiation, and neutrinos. It's with an adiabatic perturbations where delta rho I divided by rho I are the same for all species. Now, dark matter interacts with gravity and follows the perturbation over density, and photon matter interaction provides the pressure. Now, phase two, photons and baryons move radially outwards. This is the drag force, okay? And neutrinos decouple, and dark matter follows the perturbation over density, okay? Phase three, so if you want to have more information, you can go to this, just search for slides by Castander on geophysics. And electrons and photons begin to combine afterwards. Just photon baryon photon scattering decreases because electrons and protons, this is wrong, so it should be proton. Electrons and protons begin to combine. This is the recombination. So baryon photon scattering decreases and photon starts to decouple. Okay, when it decouples in phase 4, the photon decouples, sound speed drops, baryon over density peaks at a characteristic radius. Then dark matter and baryons interact gravitationally, perturbations mix, and the peak lowers due to dark matter domination. Okay, so this peak, which was very sharply peaked earlier, then basically there was this mutual attraction, and then because of the dark, we have more dark matter. They settle down up to a lower peak. Now we definitely cannot in here we cannot do everything in this notebook, because if you solve all this, and okay, you can get this correlation by doing a Fourier transform or sine transform of the matter power spectrum. Yes, matter power spectrum. But what happens is that in that case, you need to use SCAM and Cosmo in order to do the parameter estimation. But here I wanted to give you a taste of the parameter estimation using the BAO physics and CMB physics. CMB physics, for example, I already discussed with you. Cosmo MC, you know that Cosmo MC, you can run Cosmo MC. I showed you a Cosmo MC run. If you don't take the parameter, if you here you understand the perturbations are important, right? Because these are perturbations. I mean, the CMB is the perturbation spectrum. In those cases, I mean, you cannot do it in the notebook. So in those cases, you have to use not background parameters, and you have to change to theta parameters in Cosmo MC, and you have to solve it completely and then compare with the data, and then get constraints on your dark energy or any other models. But here we can still work with certain types of approximations. For example, Z star, we discussed the Z star, right? Denotes the redshift of decoupling. For correct results, we need to calculate exactly. Can somebody tell me how we can calculate Z star? Anyone? We discussed how we can calculate Z star accurately. What is the exact definition of Z star? What is the exact decoupling redshift? Remember my CMB lecture? What was the value? Anyone? Just write it down in the chat box. Value or how you can exactly determine. I defined two measures of two definitions. I provided two definitions, and one of them was just a qualitative definition, and one was a proper definition. Anyone, please? I mean, if anybody remembers something, write it down. It can be wrong, it can be right, but it is important if you remember something. Okay, there is one chat. Ionization fraction equal to 1 at ionization fraction is the electron fraction. No. Electron fraction was ionization was completely 1. before this decoupling, because in the early universe, nothing was, the proton and electron were not combined. So they were one all the time. Then what happened? Then Xe was there. You are thinking in correct direction, but I can give you the answer. But if you try, it will be good that it is connecting the dots. If you remember something, let's try to recap and try to reach to the correct definition by doing this recap, because you understood. I have discussed this many times, so you understood at that time. But there are lots of courses going on, so it is natural to forget what I was saying. So please write down. Please write down. Others, please pitch in. Guys, please interact. Please write it. Write it here. There is no shame. Good. When it dropped to 10 power minus 2, that was one of the definition. That when it's dropped to 10 power minus 2, we are saying that the recombination is nearly done. But then finally it was complete when it was 10 power minus 3 or minus 4. But we're saying that decoupling was 10 power minus 2. This is one of the definition, qualitative definition. And then exact definition, can anybody remember? We defined tau, right? Then we defined tau dot e power minus tau. What was that? Good. And G is what? Good. Okay, students are coming forward. Please, probability. Exactly. Visibility function is a probability. Probability of a photon that last scattered at a particular Z or particular conformal time, right? And what is the Z star? See, I haven't said anything. I just had given one simple hint, but you are solving yourselves. This is important. That is why I said pitch in. Yeah, this is the value. So now you will not forget this. Okay. So this was the importance of this exercise, that we discuss it and you understand. So this is the peak of that probability distribution. So where the probability, where the G becomes 1 at the redshift, where G becomes the probability reaches its peak. All right. So so sorry, I said 1, but in a normalized probability, it should be in this. It should be given in terms of the sigma, right? So when it is the position where the probability or the visibility function peaks. Okay, now in the notebook, what we are going to use, the Sugiyama's fitting function, is Z star. Okay, it depends on this. It depends on two parameters, omega baryon and omega matter. Let me just take 10 seconds. Sorry, I needed to get some water. Okay, and these fitting functions have two parameters, G1 and G2, which also depends on omega baryon H square. So you understand what we are getting towards. We had, for the parameter estimation, if you in the dark energy, we started with omega matter only. Now we are then afterwards we introduce this W of Z, and we feed that data with omega matter W0 WA. Now we are complicating this procedure, or completing this procedure, using data sets from other observations and defining joint likelihood. These observations are dependent on omega baryon, are sensitive to omega baryon, not just omega matter, omega baryon as well. And therefore, if omega matter is there, it is sensitive to omega CDM as well. this fitting function is close to the exact results from CAM. Then there is another one which is called Z drag epoch, where ZD denotes the redshift when baryons are freed from the photon drag. So this is another definition. Drag epoch is actually when you are defining this. This is in terms of not from the optical horizon. This is on the sound horizon. Okay, depending on the sound horizon. So there also you can define certain function where you can say that this is the decoupling epoch. This is the baryons are freed from photon drag. So this you can try to get it from the notebook, that which one is larger. Okay, drag epoch is larger or the decoupling epoch is larger. So I would leave it to you to just check. This is also this is obtained from a fitting function. Eisenstein who has an analytical formula for the drag epoch. This is different from the CAM's exact results. This is something that I would urge you to go to the CAM and find what is the Z drag, how it is exactly calculated. Okay, so this is certain. This is an exercise that I am giving it to you. Just try to understand it from the code. Co-moving sound horizon. Remember, I discussed this one as well. When I was writing this, I was writing the equation for the baryon acoustic oscillations in the tight coupling approach. Okay, so I defined CS as 1 by assuming C equal to 1 divided by square root of 3, 1 plus R, and when R was 3 rho gamma, baryon by rho gamma. So there A square and A to the 4 cancels, and then if you write it in terms of omega instead of rho, this A factor comes in. So CS, this sound speed is written like this with respect to the photon speed, and the sound horizon can simply be written as this. So when CS is 1, this is the, when CS is equal to 1, what is this? This is the horizon, right? But when CS is less than 1, then it is the sound horizon. Okay, speed of the perturbations, speed of the propagation, right? So of this sound waves. So there are different estimators. So this DM is the angular diameter distance and horizon, and this is the volume average distance. So there are different types of baryon acoustic oscillation observations. I mean, the type is the same. You are basically getting the galaxies or quasars from the, or the Lyman alpha forest. You get the correlation functions, and then you define certain you get some summary statistics or summary numbers, and you try to constrain that. For example, 6-degree freedom galaxy redshift galaxy surveys, or MGS, this I forgot the full name, and they provide these numbers dV by RD. Okay, and then others, BOSS gives you this low Z CMAS, low Z sample or CMAS sample, this DM by RD and DH by RD. Okay, the drag epoch. So all these functions I have defined. What you need to do is that this is an assignment that I have asked you to do. So I would urge you to plot this plot these quantities. Okay, so this is something that I had already defined in that notebook, and then you need to plot this in order to match this plot in the Eric Aubach's paper. I think I have given the link of the paper in that notebook. And CMB shift parameters. This is a paper by Mukherjee and Wang. So let's say we are trying to also add in CMB data, but we will not be able to use full CMB data because we are not solving the Boltzmann equations using CAM. We are trying to do something in our notebook, but we are still trying to get the essence of that. So we are trying to constrain dark energy using supernova, BAO, and CMB data. So we are using summary statistics from CMB data, which are called shift parameters. Okay, R and LA. So I am going to define that in that notebook. So we are going to use fitting formula for Z star and use this CMB likelihood jointly with BAO. But one thing you should remember, and these are the values for if you use Wang and Wang, these are the values, and this is the covariance matrix. So what it gives is that it gives this shift parameters obtained from analysis of CMB and then you get LA and R, and omega B is omega baryon H square, capital omega baryon H square, and this is NS. Okay, so if you have a simple model of the primordial power spectrum and the lambda CDM, and you just try to compare this with the CMB shift parameters with these values or with this covariance matrix, you can do that without solving the full perturbations theory. But this is something that is not recommended or not done at all unless you want to just check whether your results are consistent, because you already have the full solution of the Boltzmann equation from CAM and you compare with the Cosmo IMSc. Let's go back to the lab. Okay. So ZD and Z star are, so Z RD is the radius of sound horizon, and Z shift is at the redshift ZD when baryons got freed from the photon drag. Simplicity, for simplicity we are using ZD, using from Hu and Sugiyama and Eisenstein Hu, Z star and ZD. So I have defined it here, Z star and Z drag. Moving sound horizon is defined here. RS integrand, I am integrating, this is the RS integrand, C times square. So this C divided by square root of 1 plus 3 times 1 plus RB. Remember, there is this R I defined, I just mentioned here in this slide. 3 times 1 plus RB. This is the RB. What is RB? 3 omega baryon times A divided by 4 omega matter times, sorry, omega radiation. Oh, sorry, omega radiation, OMR. So omega baryon times A divided by 4 omega R. So RS is simply the integration of this RS integrand. So, and we discussed different types of estimators, right? Either dV by RD, dm by RD, dH by RD. You can take these estimators. You can simply define all these estimators, and depending on what data you are using, you can just switch between one of them. I mean, one from the other. Sorry, switch between one from the other. Okay. What I'm printing here. Okay, so I have already, so this is something that I wanted you to do, but again, I have already done it. So ZD, ZS, redshift baryon drag epoch, and this Z star is something that I have already calculated. Okay, it's from here. So just check that. And the RS, okay, is 144 megaparsec. We have found it. Okay, this is the for the standard model. Data and likelihood. So there is this 6D DF GRS and MGS BOS low Z and DVRs. For example, these are the data sets. We are using only one DV by RS data now, and DM by RS. These are the DM by RS from BOS and Lyman alpha. BOS is baryon oscillation spectroscopy survey from SDSS, Sloan Digital Sky Survey, and this is DM by RS. Okay, these are the data. You have the chi-square as well. You can simply define the chi-square of BAO DVRS and BAO DMRS, and then you can check their chi-square for this standard model, etc. I mean, but these are not the best fits. I'm just checking that whether they are giving a reasonable answer, or at least some answer. CMB shift parameters, this R that I defined is co-moving distance to the decoupling epoch. So can anyone tell me that why this should depend on dark energy? Yeah, someone was saying something. Please, I mean, speak up. I mean, or write down here. In the chat box. Yeah, I mean, it will be higher if the leg time acceleration is higher. It will modify depending on H naught and omega 0, omega A. Okay, so that means that sorry, not omega 0, W0, WA. It will change according to the equation of state. So it will depend on how much it has changed in the very late time, or let's say at redshift 1 or redshift 0.7 or something like that. What was the value of W, etc. The important thing is to understand is that, see, it is the moving distance, right? So that depends on omega matter and H naught and W0 and WA. Okay, so there are two. Okay, okay, I got disconnected. I will mail you if you have any problem raised further. Okay, repeat the question. Yeah, the question was why these values R, BAO, and everything is going to change if I change the dark energy equation of state. That is because the distance is going to change. If you change the measure of the distance to a particular redshift is going to change if you change the dark energy nature of the dark energy or equation of state of the dark energy. Okay, CMB summary data is basically, as I said, LA is the ratio between the co-moving distance and co-moving sound horizon to the decoupling epoch. So it is pi DC Z star divided by RS Z star, and this is R square root of omega m H naught square DC Z star by C. Okay. Now I define the CMB summary chi-square. I'm also just using CMB summary data. These three values, omega, sorry, R, then this LA, and the omega baryon H square. And then I am calculating the CMB summary chi-square. Then I'm writing this full chi-square here. H naught, also I'm using a H naught value from Riz et al, H naught chi-square, and SNBAO, supernova BAO, H naught, and similar is CMB summary chi-square. And then I'm writing the likelihood. So just calculating the SNBAO, supernova BAO, H naught, and CMB summary chi-square, and then just multiplying by -half. So that gives me the likelihood. All right. And then I'm calculating the best fit from there. You can see that I'm getting nearly 0.04, means 4% of baryon, omega baryon, 4% of baryon density, 30% of matter density, H naught equal to 72.4, and W0 equal to consistent to the best fit is -1.37, and WA is 1.16. So here I'm not doing any Markov chain Monte Carlo. I'm just doing a simple best fit search. You can do this Markov chain Monte Carlo at home. So there are small assignments that get all the quantities for non-flat universe, estimate the parameters jointly from supernova BAO and CMB summary statistics, reproduce figure 1 of Obog et al. That means this one. Okay, you have all the necessary functions defined here, and find the differences between CAM and this code. I mentioned that ZD is not very accurately calculated. So this is an exercise, since we are using fitting formula for ZD and Z star and how it changes. So you can simply run this with the CAM as well, using the full data, etc. And you can change, I mean, you can understand the differences. If you do these things, if you are doing your master's or PhD, you will be able to understand this in a much better way. So if you compare the CAM or class with these codes, and you can and there can be direct comparisons that, okay, I'm getting this ZSR from my code here, and I'm getting ZSR from CAM code here. But you understand that if you are just using CAM as the black box, you will be CAM or Cosmo MC, you will just run it and you will get the results. You will not be able to understand MCMC. That is why these exercises or these hands-on sessions are important to understand how things are done. You are actually doing it yourself for smaller data sets where you can solve your equations by your hand yourselves, not using something as a black box. Okay, that is why from the beginning I was not relying on AstroPy or some softwares that is automatically coding things in, or not calling cam from using Python and doing this analysis and just comparing them, just visual comparison. So you should have had some experience of solving cosmology, plotting them, getting the data, understanding the covariance of the data, and getting the covariance matrix of the data, getting, and then comparing these with the theory with the data sets by yourselves rather than relying on a black box. We also discussed why, when you just have the systematic covariance matrix, you see that we are not able to, we are able to constraints on only H naught, and then also we did it for W0, W8, etc. Okay, and moderate assignment is basically when you estimate parameters jointly with the addition of omega k. So here your number of parameters are going to increase, and then complexity is going to increase, and then you explore the model in a greater detail. Okay, so that concludes today's lecture. As usual, I took 22 minutes extra, but I hope that this will be beneficial for you. With that, let me stop and wait for questions. So thank you very much.
Sir, I had a question that is not directly related to this talk, but when we talk about inflaton or dark energy as a scalar field or something, so how should we think about the energy density stored in the potential? So should we think it like electric field, energy density stored in electric field or something like that, or it is a collection of particles or something like that? Because
No, it is collection of which particles. So we said this is a scalar field. So it is a scalar particle. Okay, you can just
yes.
think of that is it is like a Higgs boson or something like that, but it's not Higgs boson. So this is some scalar field that we have not been able to discover yet. These are at very high energies. For example, the ones that we are concerned with inflation, there was some debates after bicep 2 data that the scalar field Mars are of the order of in the gut scale, but now we are talking a little bit below gut scale, 10.12 GeV or something like that. So the energy density is simply square root of 8 pi, 8 pi g by rho, phi dot square by 2 plus v of phi. It depends on the kinetic energy and potential energy. So it is the summation of that.
Yes, yes, I am understanding that from the Lagrangian we can get the mu nu, and from there we get energy density. Calculation is all right, but so if we think about it more physically, so how should we think about it? That is what I'm asking. So, uh, so this energy,
This is the physical scenario. Just like
yes, but
a matter particle, if it is moving in an electric field, you can calculate the potential, and then potential energy and the kinetic energy because of the charged motion and etc. And you can calculate its energy. Similarly, here also you can get the force, etc. Here also you can calculate simply, just because we do not know scalar field, we have not been able to detect the scalar field. That doesn't mean that we are not able to calculate that. So here you have something that you are seeing that, okay, charged particle is moving in an electric field, so it is experiencing force. But since we do not see that ourselves, that doesn't mean that we cannot calculate. So yes, it is the calculation, and it is the simple calculation, right? That V of phi plus kinetic energy plus potential energy. I do not understand what analogy you wanted to have with the charged particle or in an electric field or something like that. Can you
so the confusion is because sometimes I read that the inflaton is told as a condensate or something like that. So those terms I really do not understand. So that is why
Okay,
I'm asking.
that is okay. So condensate or something like, we do not know, right? If you you send me that Mukhanov paper, right? You or Rahul? Who sent me? Paper by Mukhanov on the on the inflation by vector fields, vector particles. You sent me or somebody else?
Yes, sir.
Yeah,
Oh, no,
in
by
that case, you can see that it is forming a kind of condensate. But I mean, yeah, we don't really know that part. I mean, in that case, it is you can say that it is some kind of composite scalar field. And again, I said from the other example that it is some kind of composite scalar using psi bar and psi. But I mean, I do not know if you what do you mean by visualize energy, or if it is the correct, it is the term you have used or not. How do you understand? But uh, in classical field theory, this is how you calculate the energy, right? I mean, for any particle, be it a scalar field or be it some other field. This is, I mean, whenever you are talking about a particle, then you go to the field description. You you simply calculate it in the by this following these prescriptions. So exactly what you want to compare,
Okay,
I'm
sir.
not able to understand.
Okay, so it is just like a classical field, so it ends there. Okay.
Yeah. It's just like a classical field, just like a classical scalar field.
Okay.
You can
Okay.
think it as a fluid as well, right? So fluid
Mhm.
description also works. Other questions? You can ask
Hello,
me
sir.
now, or you can also
Hello, sir.
write back to me. Yes.
Sir, can you please repeat means why the increton pin cannot be a fermionic or bosonic? Why we are considering a scalar? Means you have already explained, but I did not
Yeah, so this is something that
understood.
I discussed, but there were some other questions that Orno mentioned, that there were some other papers that has either at some time earlier, some earlier time or recently, people have explored uh, uh, inflation by other particles. Firstly, what I mentioned is that simply if you take a fluid consisting of matter or dark energy, you know that these cannot accelerate the universe, right? And another thing that you can find is that the scalar field is, I mean, for example, if you take a vector field, okay, it will not be isotropic. So therefore, you cannot explain the isotropy of the universe, isotropy of the CMB. So therefore, this kind of condensate thing comes in, that you can write some kind of condensate form. You can do this with changing the coupling to gravity. So where in the Lagrangian you were using minimal coupling, where R was, there was R time R plus in the Lagrangian, there was terms of R and there was this terms of phi and V of phi. So the Einstein-Hilbert action and the scalar field action. So there, what we are doing is that we were using minimal coupling. So even if you use a composite scalar like psi bar psi using fermions, then also it is not sufficient. What you need to get is that you need to get an equation similar to the Klein-Gordon equation, phi double dot plus 3h phi dot plus v of phi. The Mukhanov paper that Ornov circulated reaches that equation, but using a non-minimal coupling to the gravity. So the R term is coupled with mu. So it is not a simple R. It has a mu term multiplied with that. Here also in the fermionic case also, this R term is multiplied with a function f capital psi, where capital psi is psi bar or psi bar times psi. Okay, psi bar psi is the capital psi, and it is, you are writing a function of this capital psi, and then you are coupling it with a Ricci scalar. Is it, and does this answer your question?
Yes, sir. Okay, I understand. Means I have.
So scalar field is the best candidate, not just the best candidate. You do not have to do, make it a composite scalar or something like that. It is inherently scalar, and then it is a minimally coupled to gravity. So in a simple framework, you can get that. So if you change the coupling to gravity, then all your equations change, right? Your Einstein's equation, etc., changes because your accent changes. So it is not Einstein but accent anymore. Any
Okay.
other questions?
Okay, yeah.
Any other questions?
Yes, sir. I had a little bit of doubt. So during inflation, it is like a scalar field, but after the inflation ends and it oscillates, so then we interpret it like a collection of particles for m square, phi square kind of inflation, because the energy density goes as 1 by a cube or something like that. So I am just confused at where this change of interpretation is happening, at what stage.
Not
So
interpretation, change of energy. So this is how the scalar field is actually decaying and giving its energy adiabatically to the particles. Okay, so there can be particle production as well. I mean, those are some things that we do not understand, we do not know. First of all, we need to understand the energy scale of inflation. We have been able to get the energy, the shape of the potential, so that it gives ns equal to 0.96, and we know the amplitude of the primordial power spectrum as well. So this is something that we have been able to understand. Then there can be preheating. For example, if you have a m square phi square model, your scalar field comes down to the bottom of the potential and oscillates. There, the oscillation shows that the universe behaves like a matter dominated epoch. Okay, and so then after that there is this preheating. After that there is this reheating, and those steps depend on different model that you choose. How your scalar field is coupled to different particles. Okay, those part we have not been able to constrain at all. So those depends on what scale the inflaton field is and how the energy transfer happens, that what is the coupling. Since we do not know anything about those coupling, it cannot be said from cosmology. Okay.
okay, sir.
Any other questions? No? Okay, then again, if there are questions, I would urge you to do this assignments. Okay, if there are no other questions, please write to me if you have any questions later on. Any confusion you have that you have not been able to understand. I assume that you are not shy and asked all the questions that you want, but I tried to I tried to break your silence. But even if there was silence and you wanted to ask some question but you could not ask, write back to me. Okay, your my email address is already given, not in the Slack channel, because I don't think the Slack channel will be active anymore after this. So now okay, so then I'm now handing over to Professor Supratik Pal. Supratik, please.
Okay, so if there is no more question, let's thank Dhiraj once again for two wonderful lectures and hands-on sessions on dark energy, just like his beautiful lectures on audio universe and CMB. Okay, so thank you, Dhiraj, once again for taking care of this dark energy aspect as well.
No
Okay, I'm
problem.
pretty sure students have learned a lot and they will keep in touch for sure.